So this is the second part of the tutorial about church encoding. In the previous part I explained why church encoding is interesting, and the main point is that church encoding is a way of encoding recursive types without explicitly using recursion in its definition. And that is a very general pattern that works in every typed language that has type parameters, type constructors, and for instance, most functional languages used today do have enough features to use it. I'm using the DOL language for examples here, but the same could be rewritten pretty much in any other functional language. Scala, Haskell, F#, Swift, and many others, and Rust as well. So the previous tutorial stopped at the point where we asked what are the general properties of the church encoding that we can see. If we focus on the formula for the church encoding that we have seen here. So this formula uses an arbitrary functor f to encode the least fixed point of f as a pattern functor of a recursive definition. So what does it mean to encode a fixed point? It means that this type, which we denote by lfix, following Wadler, the mathematical definition for that in type theory looks like this. The mu f is the fixed point of f, or mu x dot fx. One can write that as well. So this is the mathematical notation. I will be writing it here like this because this is easier in DOL to deal with. So we define this lfix as a DOL type constructor. So what are the general properties? Let's look at the type equation C equals FC. This type equation really means that the types C and FC are equivalent or isomorphic, as one says in type theory. So what does it mean it's isomorphic? It means that there are two functions from C to FC and back, and these two functions are inverses of each other. So I will denote these functions by fix and unfix. So fix takes FC and returns C. In Wadler's paper, Recursive Types for Free, these functions are called roll and unroll. But that is just a difference in names. These are the same functions. So it turns out that you can write the code of these functions generally for all pattern functors f. This is an interesting thing, and this actually shows why it is useful to write the church encoding formula like this, because it helps us reason about it much more easily than the curried form. So how do you find out this code? Well, you can say, this is just some guessing. Yes, it is some guessing, but mostly we are guided by types and by what we can compute given certain types. So the type of lfix, of the church encoding, is a higher order function with a type parameter, which means that we are supposed to take an argument, which is a function of this type, where type r is unknown. We need to keep it like that, so we don't know what r is. So given a function of this type, we're supposed to return a value of type r again. And if we are given a value of this type, then we can use it to compute values of another type, say d. If we manage to provide a function of this type, fd to d. So as long as we can provide any function of this type, we can compute a value of type D out of this. So this is a general and powerful idea about how to write code with church-encoded data. You want to get a result of some type D. All you need is to provide a function of this type. Now this function might be impossible to provide, or it might be possible. So then that's all you do. And the code would look like this. So in DOL, so you would say you compute some value of type D, and all you need to do is you provide this function fdd of this type. As long as you can write code of this kind, then this is the result. So let me go quickly through the code of fix and unfix. This is a DOL code, but should be reasonably easy to read. Because all the type annotations are explicit. Now I'm using here the type constructor functor that I defined before in this tutorial, in this book that I'm writing, not in the tutorial that I was recording. But essentially that is a type class implementation that is evidence that there is an fmap method for the functor f, and that is important, that is necessary. So how do you implement fix and how do you implement unfix? So first fix. We have a value of type fc and we need to construct a value of type c. So a value of type c means we take an arbitrary type r, an arbitrary function of type fr to r, and we need to return a value of type r. How do we do that? Well, all we can do is we can apply the given value fc to something. So to what will we apply it? Well, we can think about it. But one thing we can do with this frr that we are given is that if given a value of type c, we can return the value of type r. That we know. We just apply some value of type c to the frr that we have. The result is the function of type c to r. Well, notice we don't actually have any values of type c. We have a value of type fc. We need to return a value of type c. That's fine. Now, this is another function we can make. We can lift the c to r to the functor f. The result is a function of type fc to fr. We use fmap for that. So notice fmap has all these parameters because DOL requires you to write out all the type parameters. So the type c, the type r, and the function c to r. There are 3 parameters for fmap. So then the result is a function of type fc to fr. Finally, we apply this function to the given argument of type fc, and we get a value of type fr, which we can substitute into here and get finally the result of type r. So that is the entire code of fix. At this point, looking at this code is completely unclear what this function does, because all we have done is to juggle around the types. There's no other way of implementing this function, really. But it is not clear why it works. And this is one of the difficulties in the church encoding. You can formulate the general property, but it is not obvious how it works. What happens here is that somehow we were able to get the value of c out of fc, but actually it is going to work differently for every specific f, because it uses the functor f's fmap method, and so you can apply this function to a specific f and you get a specific function that will work in a specific way for a type, say for list or tree, that you're defining using the church encoding. It is better to look at that and try to understand how that works. But what is important is that you can write the code of this function once and for all. And similarly, you write the code for unfix once and for all. You take a value of type C, which is this lfix. So you take a value of type C, and you apply that value to the type fc, because what you want is to compute a value of type fc out of this. And so all you need is a function of type fc to fc. We call that as the general idea. If you want to get a value of type d, then you provide this function and you apply the church-encoded data to that function. So that's what we're doing here. The d is equal to fc, and the function fd to d is the lifting of fix to the functor f. So the fix was a function from fc to c. Now we lift it and we get a function from f of fc to fc. That's a very short code, but again, because of this dependency on the functor f, this code will work in different ways for each recursive type. So this is a good strategy that we're going to use. We're going to use these functions to implement all recursive types and to reason about them. So the fact that fix and unfix are inverse functions to each other is far from obvious. It is not easy to prove, not at all easy to prove. I prove this in the appendix of this book that I'm writing, and it takes me, if you see here, 6 separate steps, which I formulate as 6 different statements with proofs, and finally, after this proof, after these 6 steps, I have the proof that these are inverses to each other. So I'm not going to focus on those proofs in this tutorial. My focus is to explain the concepts and the usage of the church encoding. So the first thing that we do with church encoding, after we have defined fix and unfix, is to think about what one usually needs when one works with a data type. One needs 2 types of functions. One needs functions to create values of a new data type, and one needs functions to somehow consume or analyze values of that data type. And usually with recursive types such as lists and trees, the functions that create those values of those types are constructor functions. Like for list it's cons and nil, and for tree we can define leaf and branch as functions. And so then we write a list, for example, as cons 1, cons 2, cons 3 nil, or something like that. And so if we want to write a list like this, it means we need to have functions that take, say, some natural, and then it takes some tail list, and that produces a new list, or something like this. Now this is certainly very schematic. I'm not going to be able to define functions like this, but for example here it must be list natural and not just list, and there are other things I'm skipping But the idea is that you need functions that construct values of your type. And also you need functions that deconstruct. So for lists, usually one has pattern matching functions that finds out if the list is empty. So in Haskell you would write things like that. It is an empty list, and then there is something, and it's a list of one element, then it is something, and so on. So you want to be able to write code like this. But how do you do this when your data is defined as a church encoding, which is a higher order function? You cannot pattern match on a higher order function, and also you cannot create very easily a higher order function. It's not easy. I mean, you can certainly do that. You write this kind of lambda to create a higher order function, but it's not easy. Can we define constructors that do this instead of having to write by hand all the time this higher order function with a type parameter? So indeed, the functions fix and unfix provide answers to these questions. Fix provides the data constructors, and unfix provides pattern matching. So let me go over this briefly. So why is fix a function that provides the constructors? It is because what is f usually is a union type. So usually f, as we have seen in the examples in the previous part of this tutorial, for list of integers, this would be the f, and for the binary tree of text, this would be the f. So it's usually a union type. And some variants of this type, some parts of the union, are going to be just terminals. They have no type parameter. So that's something you can create from nothing. In other words, if C is the recursively defined type, then FC is a value that could be just nil, or it could be a value that contains some other values of type C. And because usually the pattern functor will contain some parts that do not depend on the type parameter, it means that you can create those values without any previous values of type C. So in other words, you can create a value of type FC from nothing, not having any values of type C inside. And also, you will have other variants in the f, in the pattern functor, which do require other values of type C. And so this will give you other constructors. Let me illustrate how that works. So let me show you, let me paste this in. So I'm just going to satisfy the compiler here. Right. So this is a type. Now, how am I going to create values of this type? For example, x is just going to be, I'm going to have x of type list int. So how to implement x? I need to have a function from a type. To what is this function? This function is to this higher order function. So we need to have an argument of type this function. Let me put it on another line. And we need to return a result of type R. So how do we do that? So how can we return a result of type R? We need to call this function k on some argument. We need to apply this to an argument of this type. But we don't have any values of type R. So, and the type R is completely unknown as an arbitrary type parameter. But we have this part of the union. So we can just say k and then apply this to this nil part of the union. So let me make it more clear. So I want to say nil is part nil of this union. So in DOL, in order to write this, you need to do this. So you copy the entire union type definition, and then you say dot nil to get the constructor out of it. Right? So now let me get rid of this f, and now we have correct evaluation. That means this has type checked. So this is how you would write values of this type. You would write a higher order function that takes an argument and then applies this argument to something, and you'd have to provide that something. So because the pattern functor f is almost always going to be a union type, and some part of that union are going to have no type parameters, you can always create values of those types without any further data. And then you can create values of your Church-encoded type from nothing. But also, if you have already a value, so let's call this value nil, but if you have already a value of the Church-encoded type, then you can create further values, because inside this function you need this R, but you can get the R out of those values that you have already created. So let's show how that works. So this is going to be a list with one integer inside. So how do we do that? We again write the same type signature. So it's a function from arbitrary type R, then it's a function from an arbitrary k of this type, and finally we need to apply k to what? Well, let's apply this to some x. And what is x going to be? X going to be k, x needs to be a value of this kind, of this type. So let's make, let's make a cons here, and then apply that to a record, where head is going to be integer 123, and tail is going to be a value of type R. Now, where do we get a value of type R? we get it from nil. We apply nil to R and K. I forgot one detail. In DOL, integers must have a sign. So 1 to 3 is a natural type, and plus 1 to 3 is integer. So now everything type checks. So in this way, I can define further values of type listInt. These are going to be very complicated if I define them by hand like this. So I want constructors that allow me to write this kind of thing much shorter. And that's what I develop here in this text. I write down explicitly what the constructors are, nil and cons. But you can see from this example that actually we could refactor these things into functions. So for example, this is all boilerplate except for this number. This number is the only thing that is free in this entire code. This code is complete boilerplate. So how can we derive this in general without writing all this boilerplate? Well, we use the fix function. We apply the fix function to an argument of this type, which is the nil. Or we apply the fix function to an argument of this type, which is cons. And the result is going to be either a constructor with no arguments or a constructor with one argument, with this argument. So, and with this argument of type C. So this is, in other words, if we apply the function fix to specific values of type FC, then we get specific values of type C, and all of these functions are constructors. So let's write down what it would be. I'm not going to write it down in the code. It's a lot of code to paste, and it's not easy to read here in this little window. But imagine that f is some union type. So there are some constructors, f1, f2, and then f3, and so on. And some of these constructors have type parameters and others do not. So this is a typical situation in recursively defined types. What is this function fc to c? Now, we know that a function from a union type is equivalent to a tuple of functions. So it's a function from f1 to c, a function from f2c to c, and a function from f3 to c. So the function fix is equivalent to a triple in this specific example of these three functions. Now, these three functions are exactly the data constructors for the type C defined through this f. One data constructor has no, so f1 is just a label. There's no, it's a unit value essentially. So this is equivalent to unit to C, or just C. F2 is again just a label, so this is C to C. And again, F3 is a unit type, so it's C. So in other words, we have a triple of constructors. One of them gives us a value of type C with no previous data. The other gives us a value of type C given a previous value of type C. And the third one, again, gives us a value of type C with no previous data. So these are the data constructors. So in the case of list, we would have data constructors from nil to C, which is a unit, and the data constructor from this pair to C. So from a pair integer and C, again to C. So this constructor we call nil, and the other we call cons. We can also query this if we feel like. And that's how we would usually define these constructors. But this is equivalent, as you can see, to just the type of fix. So the type of pair nil cons is equivalent to the type of fix for this particular pattern functor. That is the general property of fix. That is why it is so productive to think about fix and unfix in general for arbitrary f. Because you get at once all the constructors mechanically derived from the type of the function fix and from its code. So you can, in principle, you can mechanically derive its code. I will show in this book, once I get a bit more time, explicit examples of using DOL to derive this symbolically, because DOL is a symbolic evaluator. It can derive you symbolic code for functions, not just values computed. So here, for example, I can say 1, and it will give you, this is the code of 1 as a symbolic function. So DOL is a symbolic evaluator. It's limited in its capabilities, but it's quite powerful and not too complicated. So now that we know that the function fix is the source of all constructors, let's think about the function unfix. What does that do? It turns out that the function unfix performs pattern matching. Why? It's because the function unfix is a function from C to FC. F is a union type. So if you have a value of type C, you apply unfix to it, and you get a union type, which contains some values of type C inside, perhaps, right? Here's an example. If C is a tree, then the type FC is this union type, where the leaf contains an integer, or a branch contains 2 trees again. Now, you can just use pattern matching on this union type. You can use it immediately on this union type. So in this way, you can say, I have applied pattern matching to my type C. I have to go through unfix, but once I do that, I just can pattern match. So in this way, one can implement functions that one usually writes via pattern matching, such as take the head of a list or find that the list is empty. Right, so that's a kind of safe head function, head maybe, or that returns you a maybe with the first element, or a function that checks if the tree is a single leaf or not. It's a Boolean function. and all it does is it takes the C of type tree int, applies unfix to it. The result is a value of this type, and then you just do pattern matching. Now in DOL, this is what pattern matching looks like. There's a merge keyword instead of case or match, and then there is a record with functions inside. This is how DOL encodes pattern matching. Essentially, that's what unfix is for. So these are the general properties of this fix and unfix isomorphism. The fix gives you at once all the type constructors, all the data constructors, not type constructors, data constructors for the new type, and unfix gives you pattern matching of this type, which is very non-trivial, as you can see, as you cannot directly pattern match on a higher order function. So there's a lot of work going on in this function unfix in order to convert a higher order function to a union type. And actually you have to run this entire higher order function. You have to apply this function. You have to run this entire structure. And that means unfix actually traverses the entire structure before transforming it to a union type. So this is one aspect that you need to keep in mind. Performance is pretty bad with church encoding when you want to do pattern matching. This is general, but this is always so for all church encodings, and this cannot be improved with church encodings. If you want to just find out if the list is empty or not, you have to traverse the entire list. It's not intuitive why that is so. Why can't you just find out if it's empty or not? And the reason is church encoding represents your data structure as a higher order function. The only way to do anything with this function is to apply it to arguments. But how does this function work? How does this higher order function work? This higher order function takes this argument of type fr to r. So this is the higher order function type. It has an argument of this type, and this function applies this argument perhaps many times to something inside it. So the code of this function actually hard codes that this is applied many times to some arguments. That's how this function works. This cannot be shortcutted. It cannot be shortcut. There's no way to tell this function that it doesn't have to evaluate everything, because this function is just code. This also answers the question that you might have. Where did the recursion go? So we are encoding the recursive type, but there is no recursion anymore. So here's, for example, how you would encode a list of integers in this type using this cons data constructor. So where is the recursion? If you apply unfix to this or apply something else to this, where did the recursion go? Well, actually, that is where the recursion went. This code actually hard codes the fact that you need to apply this argument 3 times to something. So here's what happens in DOL. If you just give this function and let DOL print the code of it. The code is a higher order function that takes a type parameter, that takes some function, which is this integer to r, and then it applies that function, which is called a2 here. It applies that function 3 times to something. That's finally here there's a1. So a1 is used once, and a2 is used 3 times. This is hard-coded in a value of a church-encoded data. You cannot tell this function to perform fewer evaluations. All you can do is to apply this function, and then this function will go through all these evaluations. There is no way out. There's no telling it that, oh, actually, I just want to know if you're going to apply anything or not. No, there's no way to ask this question without providing some type R and letting it apply everything to the end and give you the result. That's the only thing you can do with this function. So this is one of the downsides of church encoding, is that the performance of pattern matching is linear in the data size. So even if you just want to find out what is the first element of the list, because of the way it is encoded through higher order functions, all you can do is to call this function, and then it will go through the entire evaluation. There's nothing else it can do. Finally, let me show you the connection to folds. Now, this is a very easy thing that is actually the good side of the church encoding, is that folds are very easy. The church encoding encodes the recursive type in a way that is immediately adapted to folding, to the folding operation. So what is a folding operation? Let's take the curried form of the list int. And you see this is very similar to the fold right type signature for lists. There's an R, there's an integer to R to R. Now R is the accumulator type. Then there's initial value of the accumulator. Then there's a function that updates the accumulator with each new integer from the list. And then finally this function returns the value of the accumulated result. So this is a standard kind of type signature of right fold. And you see it's exactly the same up to this first argument. It's exactly the same as the type signature of the church encoding. So in other words, church encoding is using the type of the fold arguments to encode the data. In this sense, you can say church encoding is just encoding the data, recursive data type, using its fold operation type. Concretely, it means that if you have a value of this type, then the fold operation on that value is just applying that function to the arguments as if this were already the fold method of some other type. So the fold method is built in, so to speak. The fold is just an identity function of this type. So the church encoding does not need a special implementation of fold. It's already itself adapted to performing folds. And so, as an example, let's show the code of pretty printing. So suppose I have a binary tree with text values in the leaves, and I want to print its text representation like this, with nested parentheses. How do I do that? How do I iterate over the tree or traverse the tree? The tree is just a higher order function. The only thing you can do is to call that function, to apply that function to arguments. What are those arguments? Well, we need to get a finally text value, this kind of text we need to get. So let's set R, the type parameter, to text. And we are going to apply this value with R equal to text. So we need a function text to text, text to text to text, and once we provide those functions, we get the result. So what are these functions? So this function is for the leaf, how to print the leaf. A leaf has a specific text value, so we need to print leaf. And then we need to print branches. So there's a left branch, the right branch, and we need to print them together. So they have been already printed. So when this function is called, the two branches have been already printed, and we just need to combine those printed versions of the branches into the big representation. So this is an important detail. So when we perform fold on this data structure, we provide functions that are non-recursive. Either a function that prints a leaf or a function that prints the branches, but the two branches have been magically already printed. So this function doesn't actually call any printing anymore. It is non-recursive. Well, clearly we can implement this function like this as string interpolation to print the tree, and finally that's what we have. So now an example, the branch with branching AB and the leaf C. So that's a very simple tree, and it's printed like this. So in the same way, we can implement many other operations, such as finding the size or depth of binary trees, or finding the size of a list, and so on. So anything that can be implemented as a fold, we can do very easily. And note, none of this looks like it's recursive. There is no recursive function anywhere. And yet we are implementing calculations on recursive data types with recursive functions on them. Usually you would implement pretty printing as a recursive function. So this is a fold which replaces recursion, but there isn't any recursion anywhere because DOL doesn't support it. So this is the beauty and the magic of the church encoding. It replaces recursion with something that is obviously not recursive and yet does the same thing. As I showed you, recursion is built in to those values. So it's hidden in there, hard-coded in some way, to traverse everything in the right way. For this reason, church encoding can only encode least fixed points. It cannot encode lazy infinite data structures, because the entire iteration must be hard-coded. So all the iteration to the end of the data structure must be inside this higher order function. This is an intuitive reason why church encoding corresponds to the least fixed points, not to the greatest or any other fixed points. But of course this needs to be proven mathematically and rigorously, and it can be done. I'm not going to go into that. This concludes this part of the tutorial where I talk about ordinary data structures and how to deal with them in the church encoding. Note that church encoding guarantees termination because all data structures are guaranteed to be finite, because they're just body of functions that cannot be infinite, so it must terminate. The DOL language uses that to guarantee termination. There is no unrestricted recursion. The only kind of iteration is this hard-coded iteration in the church-encoded values. However, church encoding can be used for many other much more complicated types, and in the next parts of this tutorial I will talk about that. This is written up in my book that I'm working on. For example, you can do type level lists, or you can do GADTs, generalized algebraic data types, or you can do nested recursive types, so-called like perfect trees, You can do existential quantifiers. You can do dependent types, even in some ways. You can also do greatest fixed points, but my tutorial will not go into that. So the next part, I will probably do an overview of those more complicated recursive types that can be encoded using the church encoding.